First, we begin with the simple equation dy dx equals ky, where k is proportional to y. In first-order differentials, the goal is to get an equation for y being related to a function only based off of one variable, x. To do this, we're going to have to integrate to get rid of the annoying rate equation we start with. So we separate the variables to each side, with dy and y on one, and dx and some constant on the other. Then, when it looks simple enough to integrate, we go ahead and do so, leaving us with some natural log function plus a random constant c that comes up when we integrate, equal to the proportional constant k from before multiplied by x, and another constant c. We can just bring both c's to one side to simplify the whole equation, since they're at the moment an arbitrary number. We will then need to get y alone, and to get it out of the natural log function, we know e to the ln of x is equal to x, so we must put our equation in the exponent of the exponential function base e. Once y is alone, we can deal with the other side of the equation, which still has the constant e to the c. This, still a constant, can be rearranged and called constant a. Now that our equation almost exactly resembles what we were looking for, with y on one side alone and some function of x on the other, we just have to plug in our known values and solve for any other constant, such as a. Since we're dealing with arbitrary numbers, I chose the initial y value at x equals 0. Then, all we do is some simple math, realizing that e to the 0 is just 1, and we solve for a. Now that we have a, there are no more constants, y is alone, and our function only has one variable. Our first-order differential is therefore solved. The graphs to the left are examples of what this function would look like if k were positive or negative in our beginning rate equation.